In this video, we're going to look at this problem right here and use the method of sections. Now, in order to save time, I already did the reactions. And so if you need to get those, you can just slow down the video or pause the video. But I'll go through these real quickly. So first of all, we want the reaction of IY and AY. And also we need AX. Now, because this is on a roller, IX is 0. So that means when we sum the force in the X direction, there's nothing else in the X direction except AX. So AX has to be 0. Then I sum the moments about I so that I could get AY. So I sum the moments about I, put 2 kilonewton times 4 meters, 3 kilonewton times 6, 5 kilonewton times 8 meters, 2 kilonewton times 12 meters, and then finally A of Y times 16 meters. Then I solved for A of Y and got 5.625. Then I sum the moments about A to get I of Y. So again, I went through that kind of quickly. Just go ahead and stop the video if you need to look at my numbers here. So finally, so now what we want to do, they want members CD and CM. So they want CD and CM. We want those two members right here. So this problem I notice has kind of a little bit of an interesting thing. If you look over here, this is two linear members here. And then this one doesn't have anything opposing it. So if you were to sum the forces in the Y direction here, you would find that OD would be 0. So like OD is going to be 0. So now, if that's 0, now if you turn this around and look at this member right here, and let me make another little sketch of that. So if we look right across here, turn this kind of sideways, you have like MOE, and we determined that this OD is 0, so we didn't even have to show it. So all we have left here is this member CO. So again, see what I drew, this and this. I left out OD because that's 0. Now, once again, if you were to sum the forces in this direction, you would see that CO has to be 0 as well. So DO is 0, which means we don't have to put in the picture here. And then when you sum the force in the X direction here, this forces CO to be 0. So keep that in mind, CO, and that's the important one. You're going to see why it's important in a minute. CO is equal to 0. But in any case, we want members CD and CM. So we can make a cut through this right about here. We need to cut through CM, which we do. And we'll need to cut through CD, which we did. So we've got those two. And so now we're going to look just at this half of this structure. And in fact, I already, just to save time, I drew this part of the structure. And again, I put in what I found here are AY values. So let me show you that left part of the structure there. So we cut through this right here. We made a cut right here. So we're left with MN, CM, CO, and FCD. And I put this was our AY, which we calculated the reaction. So again, when you do the method of sections, you're looking at this whole structure here. You're not going to look at individual joints. You're looking at the whole structure and assuming the whole structure is in equilibrium. So that means, so now again, our goal is to find CD, this one here, and we determined that CO was 0. That's what we just did a minute ago. So that's 0. And so we need to find CD. And so probably the easiest way to find CD is to sum the moments about M. So notice that M is a convenient spot because this force goes through it, so that won't cause a moment about M. And this force goes through it, so that won't cause a moment. So again, even though M is outside of our cut, we can still find moments about it. And then this distance was 4 meters. So let's do that. Let's sum the moments about M. Let's set that equal to 0. And again, we'll call counterclockwise positive. And now the only things we have are going to be this force over here. And that's going to be negative 5.625 kilonewtons. And we need to find the moment arm from there to there. And again, that's going to be this is 2 meters. This is 2 meters. And so the moment arm from M to A, remember this force that goes all the way up, is going to be 4 meters. And then we have CD, and that's going to go counterclockwise. So that's going to be FCD, and that's also 4 meters. And those are the only forces that cause moments about M. So set that equal to 0, and we get FCD is 5.625 kilonewtons. Then let's see, the other force that we need is going to be FCM. And let's see, once again, what we could do, that's 0. This actually goes through A. So we might want to sum the moments about A. Set that equal to 0. Again, we'll go counterclockwise positive. So we're looking for FCM. So again, this goes through A, so that won't cause a moment. This goes through A, it won't cause a moment. And so let's do negative FCM times 4 meters. And then let's see, what else are we going to have? Oh, I left something off of our picture here, didn't I? I was wondering, I left off, there's a force down here at the bottom, 2 kilonewtons from our original picture. So there's this 2 kilonewtons that's right down there. So I forgot to include that on here. That wouldn't have affected our moments about M because that also goes through M. But now it does affect the moments about A because it does cause a moment about A. So let's see, FCM is this way. And so this is also this way. So it looks like I might have guessed wrong on the direction. So this is going to be 2 kilonewtons times 4 meters. set that equal to 0. And we get FCM equals 2 kilonewtons. So again, I must have guessed wrong in my direction here. So it looks like that goes upward. So, and by the way, we should look at whether these are tension or compression. Like I said, this one, CM, I was showing down, but it actually points in the other direction. So it's pulling in towards itself. So this has to be tension. Then this one up here is CD was also pulling in towards itself. So that's also tension. So there you have it. Again, what made this one a little bit tricky was the fact that we needed to identify that this was a zero force member, and then in turn we could determine that this one was a zero force member. Once we did that, then we could make our cut, find our unknowns that we needed, and then we were done.